So let's add our asymptotes to this one. And the first thing we're going to do is we're just going to write that 4 on the other side so we can work from left to right. So we make sure that we rearrange our formula into the way that we're used to working with it so that we can go from left to right. If we look through this, do we have a horizontal stretch, compression, reflection, and horizontal translation? Yes, we do. Is it factored out already or not? It is. So we're already in the right form, and we can label what's going to happen here. What's this half going to do? X by 2. What's the 1 going to do? 1 left, and the 4 down 4. Perfect. So as far as our points go, we're not only going to look at what happens to our points, we're also going to look at what happens to our asymptotes. So when I'm going to label points here, we're multiplying x by 2. I'm going to label the point 1, 1, and the point -1, -1. I'm also going to put my asymptotes down. X equals 0, y equals 0. We're going to look at what happens to our points. We're going to do our points in 2 things because the x by 2 affects the x value, and then we affect the x value again. So we'll do that in 2 different steps. So in the first step, the only stretch that we have is x by 2. Now if I multiply my x values by 2, I get -2, 1 and 2, 1. -2, -1, sorry. Then when I go to do my translations, you can do both your translations left and right and your translations up and down at the same time, because one's going to affect the x, the other's going to affect the y. Some people like to do them separate, but then their arrows get really long and you have to write more. So this saves you a little bit of time. If I go left 1, my x values are going to be 1 and -3. If I go down 4, my y values are going to be -3 and -5. Now with my asymptotes, especially asymptotes at 0, well, because my asymptotes are at 0, can you see when you multiply x by 2, that's only going to affect the x1, and it's already at 0, so if you multiply by 2, nothing happens. But what's going to happen when I move left 1? It's going to change my asymptote to -1. It's not going to change my y equals 1. The only thing that's going to affect my y equals asymptote is things that affect y. But when I move it down 4, that asymptote's going to change to y equals -4. So now what we're going to do is underneath, we're going to draw a new set of axes. If you have those little sticky note graph paper things, you can use those. They're helpful. We're going to start by drawing our asymptotes. We have an asymptote at x equals -1, and our horizontal asymptote at y equals -4. We can label the points that we have. We have one point at 1, -3, and our other point at -3, -5. And since we knew the shape of our graph to begin with, and it showed asymptotic behavior going towards our asymptotes, we can draw our final graph with that as well. Yeah, I said asymptotic behavior. So let's look at domain and range of each of these. When we have an asymptote like we do in our original graph, we can say that our domain is everything but x can't equal 0. Same thing for our range. Our range is everything but y can't equal 0. Now on our black graph, can you see that the black graph, the domain is everything but x can't equal -1? And the range is everything but y can't equal -4? Now that we've seen that, I'm going to write it in the other notation. In the other notation, if I want to write everything except for -1, interval notation always starts with your smallest value. And since it goes on forever, it would start at -infinity. And it goes until it gets to -1, but it doesn't include -1, because that's an asymptote. Then it starts again. So we use a symbol called for the union of two different sets. It starts again on the other side of -1 and then goes forever. So that's interval notation for everything except for -1. Yes? Anytime you use a square bracket, that means that value is included. And so we can't have it included because we have a non-permissible value there or an asymptote. Same thing with our range. If we start from the smallest value, it starts at -infinity and goes up until it gets to -4. And then it starts on the other side of -4 and goes up forever. So in this situation, I think the set notation is a lot nicer. But again, it's good to see both. Yes? The actual equation of this, do you recognize this graph? It's a reciprocal graph. Is it a perfect reciprocal graph? Does it match up with the points that they've given? Does 1 over x work? Yes. So now, what's happened here in our function notation is we multiplied x by 2, moved left 1, and then down 4. So how does that show up in my graph? I'll write it in black. Well, it's 1 over. You have a horizontal stretch, compression, and a horizontal translation, so it has to be written in its factored form. The x by 2, right? It was x by 2. X by 2 shows up as a half, bracket, and then we moved left how many? Left 1, so that would be plus 1. So can you see how the half is where the x was in the bottom of our fraction? It's factored out, and we have a plus 1. And then down 4 would show up afterwards as a minus 4. So that would be the explicit equation for this one. I think this is a great example where the function notation is much easier to see what's going on than the explicit one. So again, what you have to think about is, and I'll use a highlighter here to help you picture it, is where's my x in my original function? And what's happening to that x? My x in the original function is in the denominator. So that means anything in that place where x was, that's going to be all of my horizontal stuff. So I just have to look on the bottom of the fraction. There I see my 1/2. There I see my x plus 1. So that way I know I'm going to stretch by 2 and move left 1. And finally, the minus 4 is outside. That way I know it's moving it down 4. But in this case, when you look at the function notation says whatever's inside my function is what's going to affect my x. And it's a lot easier to see in this example when it's inside the x. Okay, questions? Slurpee.